Okay, so here we have another Olympiad problem, and this one concerns a function f satisfying the inequality given here, labelled 1, which we'll use later, of course. So this inequality holds for all x and y in the real numbers, and our job is to prove that f of x is equal to 0 whenever x is less than or equal to 0. And we're going to use this inequality, rearrange it a little bit to try and prove this. If you want to have a go at this yourself, be sure to do it, or at any point as we're going through the solutions, if you think, alright, I've been given enough hints now to have a go at finishing the rest of the solution, feel free to stop it and see how far you can get with the question. But anyway, if you want to just watch the solution, that's fine as well, and we'll start that now. Okay, so to start the solution, we make a substitution. That is y is equal to t minus x. Okay, so we've just got some new parameter t that we're going to consider instead of y, because for all the y in the reals there is some t, such that y is equal to t minus x. So we now consider how t fits into this inequality. When we substitute this in, we get the inequality 1 becomes, and we get a slightly more useful form, we get f of t is less than or equal to t f of x minus x f of x plus f of x. Still, that term remains the same, it has no dependence on y. And then here, instead of y, we've just substituted t minus x, so we get this here. Why is this useful? Well, now we have a bound. Obviously this is t, but for f of x, okay, we have some bound for a function of the variable just by itself, because here we've only got information of x plus y in terms of y in terms of f of x. It's a little bit of a mess. So this form immediately looks a little bit more useful, and we'll work with this a little bit more so we can ultimately come to the conclusion that we're looking to arrive at. This result here becomes result 2, just so we can revert to it later. And now we're going to consider real numbers, a and b. So like I say, these are real numbers, and we're going to take it so that we have t is equal to f of a paired up with x is equal to b, and then separately we're going to consider when t would be equal to f of b and x is a, and then we combine that with result 2, and a slight rearrangement as well. We're going to subtract this term from both sides. We get that f of a, okay, minus f of b is less than or equal to f of a, f of b minus b f of b. Okay, and we also get that f of b minus f of a is less than or equal to f of a f of b minus a f of a. Then we add up the two inequalities. So let me just scroll down a bit. And when we add the two equalities, we get that 2 f of a f of b is greater than or equal to a f of a plus b f of b. Now into this inequality here, we substitute in b is equal to 2 f of a, and this becomes immediately apparent while we do this, because when you sub that into this inequality here, we get 2 f of a, f of b. Yeah, we'll leave this b alone. A f of a plus 2 f of a, f of b. And there you go. And we could have substituted 2 f of a into these and we would have still got the calculation, but for our the cancellation. For our purposes, this is all we need. So this is the same as, or 0 is greater than a f of a, and we're looking at, we want to consider x less than or equal to 0. So what can we say about a less than 0 here? Well, if a is less than 0, this implies, okay, because a is negative, when we divide by a, we're going to change over the inequality side. We can't consider a less than or equal to 0 because we're dividing it, so we'll come back to the 0 case later on. But this implies that f of a is greater than or equal to 0 for all a less than 0. Okay, and we call that result 3. That's a good start because we want to show that for any a less than 0, any real number, it's equal to 0. So if it's less than or equal, if we know it's greater than or equal to 0, if we can prove it's also less than or equal to 0, it must be 0. So now we're going to suppose that, so we'll just write that out. Now suppose f of x is not greater than or equal to, just greater than 0 for some x in the real numbers. Okay. From inequality 2, we get that for every t, so if we have a t satisfying this inequality, if t is less than x, f of x minus f of x over f of x by 2, this implies that f of t is less than 0, which contradicts inequality 3. So therefore we get that f of x must be less than or equal to 0 for all x in the reals by contradiction. Okay, and before we found that f of a for some a has to be greater than or equal to 0. Now we know that any number has to be less than or equal to 0. So this clearly implies f of a, bear in mind this was for a less than 0, so this implies f equals 0 for all x less than 0. The only thing left to consider is the case when x is equal to 0, so we're looking at f of 0 and we're going to set t is equal to x less than 0. Okay, so and setting that into inequality 2, which gives us that 0 is less than or equal to 0 minus 0 plus f of 0. So that's just f of 0 is greater than or equal to 0. But we've got this result here which we're going to call 4. So we combine that with 4 and thus f of 0 is 0, and that completes our proof. Okay, so hopefully you enjoyed going through this solution. If you've got a particular problem you want covered, let me know in the comments, and I hope to see you in the next video.